All right, I think we're gonna get started here, guys. My name is Josh Surrett, and you are in the Scaling Out with Akka Actors talk. So, what we're gonna talk about today is we have a problem, and we need a solution. And to do that solution, we're gonna set up a cluster and then talk about some advanced techniques. And there's a little bit of magic in the middle where we, discuss things. So, there's always magic, right? Okay. I am the author of Scala in Depth. I'm a big fan of Robocop on Unicorn memes, if you're familiar with those. And I work at TypeSafe, the guys who bring you Scala, Akka, and Play, where I should mention that Scala is in tandem with EPFL. But anyway, yeah. So I'm also a big nerd. Coming soon is SBT in action. After the talk, if you are willing to wait, I have stickers. And I have MEEP discounts, 42%, if you're interested in buying any Manning book whatsoever. But SBT in action should be out in a week or two as MEEP if you need to learn SBT, as I did. Okay, so the other thing I want to mention, Scala Days coming up in New York City. If you want to be a Ninja Cat, we will hopefully teach you more about Scala. So, okay, that said, this talk is in a series about the new web. The new web has all sorts of fun buzzwords in it. Big data, event-driven, asynchronous, all that kind of stuff. You're hearing about all these. The things we're going to talk about today, and I, for some reason, animated that. Event-driven, asynchronous, distributed, reactive systems. Okay, so if you need buzzwords to take back, this is the end of the buzzword part of the talk. Okay. All right. The problem, I can't scale my website. Right? I have a website and it's doing stuff, and I have issues. So this is taken from a Spring 1 talk where we're using the Spring travel system, and we were having issues scaling. So we took a look at our architecture. Right? We had classic web, service, data, database. And then we scaled out. So when we scaled out, what did we do? We made web, service, data layer twice. And then database. And we're still having problems. So we scale out. Anyone see what the issue is? Yeah. We have one database. Okay, so what we did was we took our existing service and we made a search system. So we didn't have to hit the database for searching because that was our primary use case. So we pulled it out. We made a search index where you can find hotels. We want to dynamically grow this index, be able to add hotels on the fly, have hooks when the database comes in, and saves a new hotel to go tell the index, all that kind of fun stuff. Okay? And we wanted to be able to detect system overload and return like a fail whale on search or some default result that isn't bad. Okay? So we've done this. All right, we now have an Akka-based search index that runs on a single node. Okay? When we hit the service layer, instead of going to the database, we go hit the search index. Everything's live in memory in some machine, and it's fast. Yay. Okay? It's all good. But let's dig into what we did. Okay? We're going to assume this already happened. We have a front-end portion in Akka. We have a back-end portion. These are actors. So we get a search query coming into a throttler. The throttler decides, is the system in a healthy state or not? If the system's healthy, it sends it on to a cache. The cache says, do I already know what the result of this query is from the past X minutes? If so, return that immediately. And then we go to our backend, which is classic scatter gather. We send our query down a search tree, look at topics, return responses, aggregate them together, send back the query response, and update our cache and our throttle metrics as appropriate. That's what our actor system looks like. Okay, so if you were expecting me to describe what actors are, I'm going to try to go into that a little bit here, but I need to know how many of you are unfamiliar with actor systems. Okay, great. Yeah, half and half? Okay. So these are actors. What is an actor? An actor is something where we, I thought that was next. An actor is something where we, it's effectively like an object that I can send messages to, and it can respond to messages and do work and update its internal state. The only way that object can communicate with the external world is via messages. And once I send a message, that data's gone. I can't touch it. Okay? So the benefit of this system for scaling with actors is that each one of these could run on a separate thread. Okay? They could all run on the same thread. Actors are a mechanism of dealing with concurrency that allows you to scale out very, very well. Okay? We're going to hopefully teach you what actors are as time goes on through this talk, if you're not familiar with them, but that's kind of the basic definition. Okay? So what this system is showing you is a topological view of my individual actors. Okay? Yeah, so this gather search index, we've split a bunch of hotels into what we call topics. Okay? A topic could be all of the hotels that are in, Philadelphia, and then another topic would be all the ones that are in Pittsburgh or something. Okay? Each one of these is a leaf node in that actor tree. Okay? That actor is responsible for knowing all of his hotels and for creating an efficient means of searching his list of hotels based on user input query. All right? Categories are basically groups of topics. It's an actor that sits above them. When he gets a search message, he sends new search messages down to the underlying actors and asks for their results. When he gets the response, he aggregates them together in some manner so that the most important results are at the top. So what a category is responsible for is understanding whether or not he needs to send a search query to a particular category, because you could do filtering here, and how to aggregate results so the most important ones filter to the top. In the example code, which you'll see later, I use really, really, really dumb algorithms. Okay, just the first n, that sort of thing. But that's what they're supposed to be doing. Anyway, this search thing dynamically expands. So if I have a topic that has too many hotels in it, so let's say I make a topic for all of Pennsylvania, and then a whole bunch of new hotels register with my service, I can take Pennsylvania and split it out into two halves dynamically on the fly, because the topic has some health metrics where it can discover whether or not it's too large and split itself. Okay? That's what the existing system does. And unfortunately, to walk through the code, I'm having resolution issues here, so we're going to have to do it this way. All right. So, source, main, Scala, scatter, gather. We'll look at what a topic node looks like, just to give you an example for actors, okay? For those of you who are unfamiliar. So, here's my topic node. A topic node is given a sequence of hotels in its constructor. It extends actor. Can you guys see this? Do I need to bump it? Okay. If you can't read in the back, raise your hand. Great. Okay. An actor is mostly just a receive block. Okay? Receive a search query of bad and respond with a bad response. This is a hard-coded query in the example code to show you what happens on failure. Okay? If I receive a search query where I get a query string and a maximum number of documents as an integer, okay, then execute this function. When I receive an add hotels message to add new hotels to my search index with this content, this new hotel content, I'm going to add that hotel to my local index. Okay? This is my failure recovery for the actor. Every time this actor starts up, before I'm live and can accept messages, I need to generate a search index based on these hotels that I know about. And split is an interesting method. This is where I detect that I'm too large and I need to split myself. I go tell my parent, hey, split me up, and prevent messages from coming down until the split is done. Or, sorry, send messages that are okay to send to me until the split's done and save the ones that aren't. Okay, so it's like a self-healing type system. Add hotel to local search index. These kind of things are kind of unimportant details. They're just how it operates. But the execute local query is interesting. When we get a query string, we grab the results out of our local index. Okay, this is just classic Scala If it looks like magic, it kind of is. But yeah, I'm grabbing the results out of my local index. For all of the results in this list, I'm going to yield them into a new result. And then I tell the person who asked for the query, the handler, who is another actor, this bang means go send him a message. And here's the response, which is the result out of my query. Take just the maximum number of documents he wanted. So if he requested a query and wanted 10 search results, I'm just going to take the top 10 out of this result from my local query back. Okay? So with actors, the only way to communicate between objects is this bang method, which in Java is called tell. Okay? You're telling another actor, here's a message, go respond to it. If you look in this code, you'll notice there are no locks whatsoever. I'm not synchronizing on my own state because I can only handle one message at a time on any given thread. Okay? That's one of the fundamental principles of actors. I handle one message at a time. I can only communicate with other actors via messages. And so this is where I can get my scaling. If I can fragment my problem out to enough actors and get the right granularity, I can actually keep track of state in a safe way across many, many, many threads. Okay? All right, so that's what topics look like. Yeah, actually we should go into categories. Source main, Scala, scatter gather, category node. So a category is a little bit different. He gets a set of children. So yeah, he gets a set of children that he needs to send messages out to. In his receive block, if he gets a search query, he remembers who sent the search query. Okay, that's the client. And he creates a gatherer. This is an actor who's going to get all of the responses and group them together before sending a final response. Okay? And then for every child, every topic child that he has, for each node of those, he goes and tells them, hey, here's the search query I initially got, and send your response to the gatherer. This tell method is magic in the sense that I can give a different return address for every message I send. Okay? This sender here says, who sent me the message? Give me the reference to the person who told me to handle this. This tell call here, where the gatherer is on the right-hand side, says, send the search query message to this actor, but tell him it came from that guy, because I don't want the response. He needs it. Okay? That's what I'm doing. And the add hotel basically figures out what child to send new hotels to and sends it down to that topic. Okay? This is the actor for that. And then source main, Scala, scatter gather, gatherer. This guy, essentially, he's an actor. Okay? He has a set of maximum documents that he needs before he can respond. He remembers the query, and he remembers the maximum number of responses he needs from a topic to be considered healthy, okay, from topics. So if you don't get responses from all your topics, you could still return intermediate results, and everything's okay. The way this receive works, if he gets a query response, he combines them with his current set of results. He ups his response count. If it equals the maximum number of responses, he sends the response back to the person who was listening, okay, the initial querier, since he's gathering from all the topics. And then he basically stops himself from processing ever again, takes, garbage collects himself, if you will. Otherwise, I need to wait for more data. I'm going to set a receive timeout to say if I don't get data within 1 second, there's something really bad happening, and I should, kill this and report bad data, so that we know that there's an issue with whatever portion of the tree I'm listening to, there's an issue. I didn't get responses back in time. Okay, so that's what this guy does. If I get any query response that was a bad query response, I just completely ignore it. That part of the tree was bad, I'm going to ignore it. I'm still going to try to return good data. Okay, so this is what the gatherer does, essentially. I'm just listening to the responses from n number of topics, joining them together, sending them to the parent. Okay? I assume this is clear as mud because I forgot to put intro to actor slides in. Awesome. Okay, so now let's get into some more advanced stuff. Our front-end query cache that we had, okay? This caches the top-end query results. It invalidates query results and requeries every once in a while, since your search cache might change. And he's the primary result of our speedup, is just caching results of queries. This is the thing that has to live and be very, very fast. The throttler basically records average response time from the whole search query. And if that response time gets to be bad, then we switch into a failure mode where any query that comes in, we immediately respond with, hey, the system's overloaded, we can't access you right now. Why? Because users appreciate results. They don't want to see the little spinning data. So if we can't respond within like 2 seconds, we need to make sure that the user knows that there's an issue and doesn't continue pressing the button and overloading our system, right? It's a circuit breaker. Okay, so let's remember what this all looked like. All right, here's the scatter gather. When I get in a search query, I send it down to subcategories. They send it down to their topics, okay? This is how the messages flow. These messages then come back asynchronously from the topics whenever they figure out what's in their index. And the category, or I should say the gatherer, sends those messages back up and we send the results to the user. But what's actually happening with the gatherer, when I get a message, pressed a button. When I get a message and it comes down to a category, I create a gatherer to handle the results, okay? And then I'm out of the picture, I don't matter anymore. I can handle other messages. When I create the next category, I create gatherers. Every time I hit a category, I create a gatherer. And then the results feed back the gatherer stream and go back to the client. So why is this important? For those of you who are unfamiliar with actor systems, the only way to track client state is to create a new actor. To track a transaction as it flows through the system, you create an actor to remember the transaction, to remember that state. The only way you can save state in an actor system is via actors, okay? The benefit of this is while these topics are responding, I can have another query start to flow down my tree. So I can have, this tree can be responding to multiple queries at the same time. They all are in a pipeline, but that's still possible, okay? I start to get some parallelism. All right. Throttling, the way this guy works, we get in the message to the throttler. The throttler creates an interceptor to remember when the query started, who it came from, and who it needs to respond to, okay? The query comes down through to the search tree, comes back to the interceptor, assuming things are okay, and the interceptor immediately sends a response back to the user. Sorry. Too long a delay on my animation versus my talking, and sends some statistics information to our little throttler statistics service, okay? All right, so if I get a timeout, I create my interceptor, send down my query, and Akka tells me, hey, 2 seconds passed, something's bad here. I tell the statistics service that there was something bad after I send the bad response to the user to make sure the user isn't waiting, okay? Now let's say the statistics service determines that we've failed too often, the system's in trouble. What I can do is I can send a fail message to the throttler, and it flips state to a fail state, okay? The actor has now changed the message handler that it uses. So when a query comes into the throttler, I respond, hey, we're in a bad state, things are bad, stop sending queries, we'll be up soon, okay? And then after some amount of timeout, the statistics service says, hey, let's try again, see if the search service is back and running. We flip the state on the throttler by sending an allow message that it responds to and changes its behavior again to respond to message differently and can take queries again. So what this is doing, what this shows you with actors, is that actors can become different things. Okay, actors are stateful. That message handler that I showed, that receive block, I can actually change it dynamically based on what's happening in my system. Okay, I can react to the environment. I can keep track of what's happening and react appropriately. All right? Now this all gets fun when we start to cluster. So we took this actor system. We have this tree that dynamically expands. We're using all 24 cores on this system. We're just maxing everything out with these queries flying back and forth. And now we can't scale the actor tree. It's the same bottleneck we had with our database because it's one thing. Okay? So now we need to scale out. We need to cluster. So how do we do that with Akka? So this is what we tried, and yeah, it's better because the search index is just sitting in memory all the time, but it's still not good enough. So what we want is we want our Spring application to live beside our Akka search index node. That is a live node in an Akka cluster, okay? And then a React database. Why are we using React? We're using React to keep track of the search index. So if we dynamically break it apart, we need a highly available database that can remember what we did, okay, and keep things up to date. Why did we choose React? Well, because React clusters almost exactly the way Akka does, because Akka was designed based on React. Okay, all right, so yeah, and then I want to be able to start adding cluster nodes and have this thing start to scale, okay? So assuming we understood what happened before, which I'm not going to assume, but play along with me. Okay, assuming we knew what happened with the system before, how do we start adding cluster nodes and scale with Akka? Okay, how do we make sure our software is appropriately fragmented? So we're going to use Akka clustering. It now supports automatic clustering, membership, notifications, all that sort of thing. It's experimental in 2.1. I'm using 2.2 milestone 2. Where it's still considered experimental because it's a milestone release. Okay? I don't know exactly when 2.2 will be released, but I know that when it is released, the first step of clustering will be there. Okay, the first. And the primary reason why it's experimental is about failure detection of nodes when a node is down and making sure that all the failure messages get out. Okay, so that's the thing we're making sure is stable, and you'll see why later. All right, so let's identify the portions of our application that can scale out, that we can move easily and effectively, okay? But before we do that, first we have to set up the Akka cluster. All right, so we add library dependencies. We already depended on Akka before. Now we just add a dependency on Akka cluster experimental. Hopefully when it's not experimental, it won't have the dash experimental. If you need to know whether or not it's experimental, it's whether or not it's called dash experimental. If you're in Maven, it looks a lot bigger. So, okay. After you do that, we need configuration in our system, our Akka config. So the way that Akka clustering works is you take an existing Akka application and add new config, and then it can be clustered. That's the goal of Akka. I can take a system that works on a single node, change my configuration, and all of a sudden it's distributed. Okay? Sort of. All right. So I changed my provider to be a Akka cluster ref provider. What this is doing is, if you saw before when I was sending messages and things to actors, there's a thing called an actor ref, which is essentially a pointer to an actor. I have to tell the Akka system that this reference could be someone local or someone remote. That's what that does. All right. Next up, I set up some logging and what my local host name is, which in this case I'm using localhost, and I'm just starting up 30 processes on a big machine instead of using EC2 because I was worried about demoing on EC2. So anyway, okay, localhost. And then in the cluster, you set up seed nodes. The seed nodes are the nodes that whenever someone wants to join the cluster, they're going to go talk to these two guys, or you could have 3 or 4, however many you need. They're going to try to talk to one of them, and the first one to respond, that will help them start entering the cluster negotiation, hey, I'm a member sequence. Okay? So these are just 2 nodes that you need to know about to join the cluster. So you have, unfortunately, you have to have someone hard-coded, but that's how you get automatic joining then. When the node starts up, hey, which one of you can tell me about the cluster I want to be in? Auto down is whether or not we automatically mark nodes down. That's the failure detection stuff. Okay, so anyway, we update our configuration. Yeah, actor references, what node we need to join the cluster. Here's what our code looks like now. We create our actor system that we use to instantiate new actors in Akka. That's it. It doesn't change, okay? So remember our actor layout that we had from before with our front end and our back end? Well, what we want to do is we want to look for ideal candidates to scale out. Well, we have a front end and a back end. Let's look at the front end. Maybe we can take the throttling and the cache and move that onto every single member of the cluster. And then when messages come in, we can just, send it to a different member of the cluster and have a local cache that can immediately respond, and have a local throttler that can immediately respond to know whether or not the underlying things are dead. So we're going to replicate our cache everywhere. So yeah, this is our creation of the front end. We system actor of the front end actor. That hasn't changed for clustering. It should be the same, ideally. Okay, so this runs on every cluster where we want a front end. The downside is that search tree is only running on one node still. So anytime a new node joins the cluster and he starts up a front end set of actors, we need to tell him where the search tree is. So what we do is we create a register search tree method on front end instead of directly passing him in. And the front end will get a message that says, here's where the search tree is now. Send your queries here. Okay? So we can dynamically change where the search tree is by reference. And then we have to make the back end tell the front end where it is when it starts. So the way we do this is, instead of having the front end listen to the back end, we have the back end, since it's running in one spot, listen to the cluster and say, anytime a member joins the cluster, I know there's going to be a front end on there. I'm going to send it a message to tell it where I am. Okay? So here, when I instantiate the search tree, I need to grab some cluster-aware code. All right? The way we do that in Akka is the cluster object can take in the actor system and return you the cluster associated with that actor system. In Java, you would have like a factory, and you would pass cluster aware factory and pull all that junk out. Yeah, this is what it looks like in Scala. Okay, before we start the search tree, we subscribe to the cluster for any time a new member joins. Before we stop, we need to make sure we unsubscribe so we don't have broken references. All right. By the way, this is a new actor called search top. What we're going to do to prevent the single node instance from breaking is we're going to create a new actor above our search tree that is the one that registers with cluster of where we are, and he's going to delegate down to the actual search tree. So that's what this search tree guy is doing. Okay, so he's the new top. When we receive the member up event, you can see when we get a search query, we just delegate down and send it on to the search tree. But when we get a member up event from the cluster, this is a new cluster member. So we need to go look up. We grab the root actor path for that member's address. Member.address returns the actual IP address and port for the member. That's how all of Akka works. The root actor path is basically it's a string of like IP, port, actor system name, that sort of thing. Anyway, we're making an address for the search front end here, okay, with root actor path, and then we're sending the register tree method to it. The thing you need to remember is that member up is automatically given to us by those cluster events. Anytime a new node joins the cluster, we get member up with the address, and we go say, hey, that new front end tree that's part of this new node, here's some information you need to know. We're registering with the guy. All right? So here's an example of what we have now. We have our search tree, the scatter gather. We added a new top actor above it. I start a new cluster member number 2 with a new front end. After he joins the cluster, after cluster consolidation is done, he sends a member up notification, which ends up going to that top actor, because he's a listener, as a message. And then, oh, sorry, skipped. After that, come on, animation. Anyway, he sends the register tree to that front end. He looks it up using the address that was part of the cluster aware thing, sends the message, the front end creates the cache and throttle pointing back at top. So messages will flow from the second node back to the first node. Okay, so we've just scaled these guys out. All right, so the member up message just fired, and front end still finds the back end. Oh yeah. I didn't show what happens on the original node, right? The node where I'm running my search tree, I actually don't have to explicitly register the front end with the back, or the back end with the front end on that node, because when that node comes up in the cluster, he's going to send his own node up event. Everybody in the node sends a member up event. Okay? So the search tree just has to listen to these events, and he'll even get local member up events. All right? So that handles everything, all my wiring, if that makes sense. I hope that wasn't confusing. Okay. All right, so to recap, I can use cluster membership notifications to communicate state across the whole cluster as needed. So anytime a member comes in, I can go tell actors on that cluster, hey, here's the information you need to join the system. Okay? Anytime someone joins, I can also listen to member down events and remove things, that sort of deal. All right. So step number 2 is, now we have our cache and stuff running on all these nodes, so we've scaled out part of our system. Step number 2 is we need to have the search tree actually survive failure. So if a node goes down, I need to know to restart it on a different node. So what we're going to use here is what's called the cluster singleton pattern. This is where I want an actor running on one instance in the cluster at any given point in time. And if that particular instance crashes, I want it to move somewhere else in the cluster. Okay? Now the way that we do that is we construct a manager on every node. Every node has a manager instance just waiting. And in case of failure, and this manager becomes the leader, he says, oh, hey, I'm the leader now. I'm going to reconstruct the search tree, essentially. He's the one responsible for recovering from failure. And he's the one, the manager is the one that contains the actual search tree, essentially, on a single node. So on leader failure, a new leader is chosen, and that manager creates a new leader. Then what we do is we create a local proxy beside the manager. So on every single node, we have an actor, which represents the singleton node wherever he exists. Okay? Anytime we elect a new leader, we need to redirect messages to the actor on that leader, because wherever the actor was died and he moved, and now messages have to go there. So we create a proxy, someone who sits in the middle. So when messages come to the proxy, he sends it to the current leader, and he keeps track of that state for us. Okay, so this is part of the pattern. One of the issues here is there's a bottleneck with the singleton pattern. You have one actor handling everything in your cluster, all messages coming to it. All right, we'll deal with that next, how to help take away some of the bottleneck things. And the other issue is there's a delay. If a node crashes, it takes us a certain amount of time to detect it crashed, and then it takes a certain amount of time to renegotiate a new leader. I mean, renegotiating a new leader is actually pretty fast, but relatively this can be slow. So the amount of time it takes to handle failure and reconstitute your tree is somewhat significant. So you still need those throttlers and that base error response so that the failure recovery happens. And there may be alternative solutions you can look at, but still, for a lot of situations, this is a good solution. So we're going to use it. Here's how we do it. When we instantiate our search tree, okay, the top of the search tree is this node manager over here. All right, this is actually how we instantiate our search tree. But we put it inside a cluster singleton manager. The cluster singleton manager, we give it a name where we can look up that actor, and we give it a termination message. So in case I need to kill the current leader to move to another leader, I need to send it a message. Okay? And that message here is the poison pill, which is the default actor kill message. I could send a custom message if I wanted to save state so the next leader could restore the state. But that, again, is dangerous because if the reason why I'm moving to a new leader is that the node crashed, I just need to be able to restore from state anyway. Right? Anyway, and then I give this guy a name. So this is how I construct the managers. And I do this on every node. So every node in the cluster creates one of these actors. Okay? Create a new node manager. And here's the configuration for the Singleton manager. All right? This is the actor that I'm creating, and this is the configuration. All right. Then I create a proxy. The proxy is an actor that registers for cluster events, and anytime the leader changes, he updates the leader address of where to send messages now. So if the cluster has chosen a new leader, I get a current cluster state of whoever the leader is. I update my leader address to point at that guy. If the leader has changed, I update my address to point at the new guy. And then if I get any other message in my proxy, I look at who the leader is now and send it to user singleton search tree. Okay? User singleton search tree. If we look back at the config here, name singleton, singleton name search tree. Okay? The path that I'm going to use to look up things is the name of the managing actor on a particular node in the cluster, and then the name of the underlying actor on that cluster. It will only exist if he happens to be the leader. Okay? So this is a proxy, and this is a bunch of annoying boilerplate you still have to write in M2, okay, to have the proxy. But this proxy, again, lives on every node, and this is the one I send messages to, and it will reroute to where the current leader is. So what I've done, I have a proxy and a manager on every node. Okay? When I get a leader changed event, it goes to all nodes in the cluster. All right? Conceptually. The manager, who is now the leader, creates my search tree, restores it from my React database. All right? And then my proxies go and look up that guy and say, oh, hey, here's where my messages are going to go. They go to that guy on this node, and then anytime I get a message to the proxy, it redirects to that search tree on that node. So now if this node were to fail, I would get a new leader message to this cluster, and I would reconstruct the search tree over there on that node. So now I can survive a single machine failure. Okay? I've been talking really fast and going really fast. Anyone have any questions so far? Yes?
So if node 1 goes down, how does node 2 know to go down?
That's a really good question. So what we actually do, the question is, if node 1 goes down, how does node 2 know that node 1 went down? So there's constant communication happening between all nodes in the cluster. And we're measuring the response time. Okay, it's, we send a message every n whatever, and then we calculate how long it took for the message to go and come back. And we track the average, okay? And it's this phi accrual method. So there's this kind of a graph that happens on failure where you'll watch, we calculate the percentage that the node, a percentage guess of whether or not the node is down, and there's a threshold that you can set in Akka to say, I want this, I want it to be, like n% when I say, oh, there's a failure. I'm actually using the wrong math to describe it, but essentially what we do is we use the average response time that we just got back to determine the percent likelihood that the other node crashed. And if it's over the threshold that you've configured, we say, yes, it did crash, kill that thing out of the cluster, and he has to actually rejoin with cluster membership later to become part of the cluster again. Okay?
So that's something you do internally, you don't have to.
You don't have to do any of that, yes. And you'll get messages notifying you. Yeah, that's the beauty of this new clustering support is you don't have to worry about nodes coming up and joining. You'll get notified. Akka's going to handle the details. You do have to configure this threshold because if you're on if you're running locally versus if you're running in the cloud actually has a little bit more of a lag time sometimes. The network is a little chatty. so you might need a higher threshold to avoid actually killing nodes and restarting them, right? So you might need to know a little bit about configuring, but the tuning is going to be pretty light, relatively. Okay, all right. Yeah, so if we get another later changed event, the manager is going to stop that actor, assuming this node is still alive. And we start up the actor tree over here, and relook things up and rewire our application, okay? All right, so now we've fragmented out our cache. We can handle, failure. We can recover on failure, but we still don't have really good parallelism of our tree, right? So we need to fragment this sucker out. And when we look at the tree, we look at the most significant piece of the tree, for our use case, we're going to assume that those topics, that local search index, is actually memory intensive and CPU intensive. And that's the thing that when we want to fragment across the cluster, we want to fragment our topics. The categories actually are rather efficient. We have a good algorithm for mixing things because we don't care. We just take the first 10. Yay. But the actual topics take a while. So, yeah. Here's our scaling issues. If you look at this, you can obviously tell we have our cache and throttle on every member of the cluster. So we got lots of good parallelism, but search tree is still bad. So let's fragment him. All right. We're going to use routers in Akka. For those of you who aren't familiar with routers are a layer between when you construct an actor and you get back a reference to an actor. A router is a layer between that reference and the actual instantiation of one or more actors. So I can create different types of routers, like a round robin. So when I go to construct an actor, I say, construct this actor, but give it a round robin router, and make 5 instances of the actor, and then send messages to each one in round robin fashion. So it's a way to fan out my actors in a way that's kind of invisible to you as a user. All right? You can take any actor in an Akka system and add a router via just configuration. You can do this completely without code, essentially. Anyway, so here's an example of non-clusters. We can do round robin. We can do scatter gather, which is the first to find something and respond wins, and that's the response you get. So I will send queries to a whole bunch of actors. The first one to tell me a response, I fire off that message and ignore the rest. Consistent hashing is where I take the message and I hash it, and that hash determines which actor to go to. And for the same message, it will always go to the same actor. That's actually a really beautiful one. Random is, we just randomly send it to an actor and don't care. And broadcast is I set up 5 different actors to handle the same message every time. Okay? Or n actors. All right, so these are what routers are. Essentially, it looks like this. Let's say I create a round robin router with size of 2 for my topics. When a category constructs a new topic with a round robin router, what he gets is he gets a reference to this little piece of code that is a router. It actually is an actor, but it's a router. And then I have topics underneath. So when the category sends messages down, it hits the router, and the router determines which topics to send messages to. Okay? All right, so in the cluster, we have clustered routers. So I can actually create an actor, and I don't care what node the actor lives on. I can split it across many nodes. All right? I can shard these things out. So here's what it looks like for our system when we create our new search router. I'm creating a broadcast router with 1 instance because with my topics, they're rather intense. It's a lot of data. And I only want one of these guys living on any particular node. Okay? So with a cluster router, you create a local router and cluster configuration to spread that thing across the cluster. Okay? So here I say I want 3 instances total of this topic in my cluster, and I want the maximum number of instances on any particular node to be 1. All right? So what this will do is it will create 3 instances across my cluster with only 1 topic on any particular node. All right? So now what we have is this. I have my category, I created my router, and when it creates the actors, it will create topic 1, 2, and 3, instance 1 and 1 and 2 here on this node, and then that divide is a separate node. The rest go on another node. So now every time I create a topic, I start fragmenting pieces across my cluster. I make sure there's only 3 ever, and there's only 1 on any particular node. So now I can start fragmenting things out. The assumption here is that, again, sending a message to a topic takes long enough to be worth the network hit of going across a node, but I've now kind of scaled out my system. I get better parallelism. Okay? What's cool is these are being added now. There's this adaptive load balancing router. So I can have the router decide what node to send it to based on cluster statistics. The service that we had to watch cluster membership and leader election and that sort of thing, you can actually watch statistics as well. And so we use those in the router to listen to heap statistics or CPU statistics or at load. Or mixes, basically, we listen to all of them and pick whichever one has the best values. But I can route to whatever node has the least CPU or the least memory or the least heap usage. Okay? So if I'm sending a message that I know is going to actually add to the heap, say like add topic, I want to use heap. If I'm sending messages that are going to consume a lot of CPU, I can use CPU load balancing. Okay? So that's the next thing that's happening with routers. To recap, this is a little bit about clustered system design with Akka. Okay? We're looking at Akka 2.2. We're looking at the new features that are coming. And we're looking at basically how do I take an existing actor system and parallelize. Okay? Everything I showed you today that I was doing with code, ideally, all of it will be in configuration in the future. So you can write your application with actors on a single node, test it, verify it, and then add a new config file that explains how to portion things out on a cluster. One piece that was added from between when I started trying to write the talk and when I actually finished writing the talk is cluster membership roles. So if you look before, here where we defined a router to just send topics anywhere in the cluster, that might not be ideal for your circumstances. What if we wanted to take this set of the cluster and make it be the search index piece, and this set of the cluster and make it be the front end piece? Or we want the front end everywhere, but we want the search index only over here. We want some other service over here on these nodes. Well, there's actually now roles with clusters. When I start up an actor portion, I can give it a role and call it search index. And then I can make sure that these topics only run on that role. Use role, some search index role. So as long as this is telling it to only start that actor on a node that has a given role. When we saw the Singleton pattern can run based on role leaders. So for these nodes that are in that role, there will be an instance only in that set of nodes. So I can have a bigger cluster that's fragmented by roles. Okay? So that kind of stuff is coming in Akka 2.2. 10 minutes, thanks. Okay, so to recap actor systems in general, actors are all about partitioning the state of your system into small pieces. That's the primary way that we get a big concurrency boost. Okay? We communicate with immutable messages. Once I send the data, I don't touch it. The other guy gets it. He does whatever he wants with it. Spawn new actors to track temporary state. That's kind of the way that you handle any sort of transaction or session within Akka. We design our whole system as a topology. The whole time I was talking, we were looking at trees, and this guy talks to these guys, and you're looking at things from a top-down view. All right? And then we partition our threads essentially on that topology. We partition our error handling across that topology. We bubble up errors. I didn't talk about fault tolerance a lot in this talk of individual actors. We talked about it across nodes, but essentially the way Akka works is if there's a failure on a particular actor, it tells its parent, and then he can decide how to handle that failure. Across nodes, if a whole node goes down on one cluster, you get a whole bunch of these errors pop up, and you have to figure out how to reconstitute that entire portion of your search tree or whatever was on that cluster. The beauty of Akka is you design this from a single-threaded perspective, and then when you hit clustering, it's not that much different to restore. Okay? All right, so with clustered actor systems, we're now taking that topology and we're partitioning it on our nodes. We're figuring out which pieces to throw where and how we want to fragment out our program. You want to limit the instances of things using routers. So if I don't want to start something on every node in the cluster, right, I can limit it by using that clustered router aware stuff and say, I only want 3 instances in the cluster. That's the max I'll ever need kind of a thing. We can register with other nodes and actors and things using cluster listeners. Everything I do in the cluster needs to be reactive. A new node came in, a new leader was elected, this node went down. Everything I do has to react to what's happening in the cluster. I don't make assumptions or think I can go read the state. I just react to what happens. Okay? We use roles to fragment actors across the cluster. That's a new one that I didn't really have time to dig into. But essentially, you can take your cluster and partition parts of it for roles where, this subcomponent exists in this portion of the cluster. Okay? And then we can keep singleton actors on either a leader or on a role leader. The role leader is just within a set of nodes with a role. He's the leader for them. Okay? But it's the same concept that we saw before. There's role leader election that happens at the same time as leader election. All right, so this is how we partition our topology, taking the actor graph and split it apart. These are the tools that we have right now in Akka 2.2. You want to avoid excessive inter-node messaging. I mean, that's big on any distributed system. If I'm going to fire something across the network, it better be worth it. I better not be sending 1 and expecting to get back 2. And it's always going to be 2 because that actor only adds 1 to things. That's a useless network hit. Make sure it's significant. Make sure when you figure out how to split these things apart, that you're splitting apart in big portions. Okay, one of the dangers of Corba that kind of killed it was that it was really easy to make really, really fine-grained distributed network communication, even for local things. And so people overdid this, and then your system falls apart because you're doing too much network traffic. It's also a danger in Akka because it's so easy to instantiate an actor and send a message. That's how you do everything. It's really easy to just send. You could have a cluster of 5 nodes with 5 actors on each node, and it's really easy to do that, but it's not necessarily the most efficient thing. Think about where and how you take portions of your system and send it to another node. Okay. So you can use statistics-based routing to figure out how to send things to someone who is less loaded and will be able to respond in time effectively. And you want to fragment in big pieces. All right? And finally, remember that it takes time for the cluster to converge and to detect failures. So you need to have these kind of health metrics to know, hey, the system's down, I need to give it time to recover. What do I do in that case? Right? All right, so key point of Akka clustering. Ensure your system can recover from failure when you write it in a single node use case. And clustering actually isn't terribly difficult to then take things and start fragmenting them with configuration. As long as you can recover from failure initially, it becomes a lot easier to deal with cluster-based work, where failure is even more likely and more fun to deal with. Okay, here are a few resources. The source code is at JSurret Intro to Actors if you want to read the source code that I used for this talk. I don't really have time for a demo, sorry. And Akka.io is the Akka concurrency framework. Inside of there, you can read there's a cluster spec, which describes all the algorithms that are used to determine cluster leaders, all of the terminology that we use in Akka. And there's also documentation for how to use the 2.2 clustering system. So everything I just showed you is available in a really well-written set of documentation. So with that, Any questions? Yes?
Are there any tools to monitor the health of the cluster?
So the question is, are there any tools to monitor the health of the cluster? There is the cluster statistics service where you're monitoring the different stats and things. So you can actually set up a listener to listen to that and then just monitor it directly. I don't think there's a specific tool for clustering. There is the TypeSafe console, which is a tool for monitoring actor-based systems, but I don't think there's any I don't know what you would need beyond the stat service to implement such a tool, and I don't know when the tool will exist or if it exists, so I'm not sure. But I know the stats service basically gives you what you need to monitor the health, essentially, of the different pieces of the cluster. So you can just listen to him, and it'll tell you, here's your CPU, here's your memory, that sort of thing. Yeah. Yes?
I had the same question, I guess I'll come up with another one. The concepts you covered today ring the bell probably for the ones who work with messaging platforms.
Yeah.
Managers, brokers, topics, subscription. So how does this compare, how does Akka actors compare to, let's say, I don't know, platform that is built on top of Java messaging, let's say, something like that. In your view, I guess it's tailored for the Scala, but what would you say the main advantages versus the, let's say, system-based messaging?
Okay, so since I have to repeat the question, I'm going to shorten it. But the question is essentially, how does actor systems, actors are very message-based, message passing. How does it compare to like JMS and existing Java message passing solutions? Did you mention message-driven beans or not? Okay, like message-driven beans. All right, so primarily message-driven beans, I really hate them. Having used them for a while, they just are annoying. But the main thing that's different between actors and message-driven beans, you can have n instances handling messages. With actors, only one message is handled at a time by an actor. So you can actually keep them stateful. They're very stateful. They're all about state. Okay? So that's the big difference between JMS and Akka, is that a Akka actor can only handle one message at a time, and it's only running on one thread at a time. So if you want parallelism, you actually have to use a router to create n instances of it, which means that you have to be able to have n instances of the same state and not die, right? So it makes you aware of these kind of things. The difference between it and like a JMS solution is basically the amount of overhead, okay? Akka, internally, for internal messaging, is very, very fast. Very fast to send a message from one Akka actor to another. The overhead of creating an actor is very low. You can create, a billion of these in a JVM in a, decent-sized box, right? So the fact that the overhead is so low means that you can use it for the small part of your application, and then when you decide to move a portion of it remote, then you incur the overhead of actually serializing messages out, having an API and that sort of thing. But the overhead is still kind of lighter weight because the whole system is designed for that, right? With JMS, you have like guaranteed delivery. That's crap, okay? Guaranteed delivery is, in my opinion, a useless thing. Even when I've had guaranteed delivery, I still have to act things to somebody else. It doesn't matter if he guaranteed to deliver it. It doesn't guarantee I can handle it, right? I still have to act to say, hey, not only did I get it, I handled it, things are okay, stop sending it to me. So guaranteed delivery, you almost always have to implement send-act functionality yourself anyway, based on your application's needs. So with Akka, you don't have the overhead of all the guaranteed delivery guarantees. You can just do send-act, and it turns out to be more efficient in the long run. So yeah, when it comes to Akka, it's very, very, very lightweight messaging, very, very lightweight actors. Really, really easy to make tons of these and design your whole system with them. With JMS, it's heavyweight. You need to be careful with how many JMS receivers you have. You need to make sure they do a significant amount of work for them to be effective, et cetera, et cetera. So it's a very different paradigm. Very different paradigm. Not that I don't like JMS, right? It's very effective. In fact, you can use JMS to connect to Akka actor systems. and send messages via JMS. That's fine. But Akka is much, much, much lighter weight and smaller. I think I'm over time, and we're getting kicked out. But I'll be outside if you want to chat with me out there. Thanks, guys.